Hello. You should see the desktop and you should be able to hear me. Does everything seem okay?
Yep.
Okay,
Yep.
great. Thanks. Okay, let me bring up the chat window. Okay. And, okay. I think I got everything ready. And okay, so what we're going to do today is look at, we're going to start talking about pointers, and we're going to use pointer. Well, we're going to start talking about some more stuff that's involved with your homework assignment, but there's some things that we have to, I want to talk about the scanf function in particular and how it uses pointers. And the C language and pointers are going to be real important in this class. So this chapter here is really good. Let me show you. The reading assignment is this chapter on pointers from this book. It's pretty good. This chapter I would really recommend you read. The other chapters I thought of as kind of like read on a need to know basis. Like if you felt you needed to understand something, go look at the chapter. But this one, everyone should read it because we're going to make use a lot of pointers. And at the end of that chapter are some just exercises that are real good. There's about 6 or 7 problems here. So it's like 7 problems that are really good problems to work on. Okay, these are exercises. They have short answers. You read the code and you say something about it. Then there's what the book calls problems are right programs. If you want, you can look at those and think about them. But you'll have plenty to write with our homework assignments. But these are real good for you to read. These are short little snippets of code where you have to understand what that's doing, and you have to understand what that's doing. Okay, so these are good. That's just 2 pages, 7 problems. I think you should do those too. So that's actually the at the end of chapter 6. That's at the end of this chapter. Okay, so we're going to need pointers a lot. You can't write C programs without using pointers. You especially can't write systems programs, operating systems programs, without using pointers. Okay, I mean, you can take a course like CS 124 and probably not use pointers for a whole semester, but that's just because that's introductory C. Once you get to real C, where you really need to get things done, pointers and memory allocation and dereferencing pointers is just going to become more and more important to us. And in pretty confusing ways, the C language and the Windows operating system, they use pointers, pretty elaborately. We'll see especially when you get to homework assignment 2, you'll see how elaborate this stuff can get. All right, so that's your homework assignment that's your reading assignment is to read chapter 6. Okay, and what we're going to do is there's more examples in the homework folder, and there's more examples in this we want to look at today. Okay, so we're going to look at just some more examples of C code in these 2 folders. Okay, I can unzip this one. This other one's stalled. Wonder why this other one's taking a long time to download. I'm gonna go ahead and cancel it and try it again. A lot of times it's faster just to cancel it and try it again. Bingo. See, it probably would have sat there stalled for days, but canceling it and starting it over again a lot of times just fixes it. Okay. Oh, now before I open these, has anybody got any question about the homework assignment? You've had it for a while now. Has anybody seen anything in the homework assignment that they don't understand, or anybody want to ask a question about the homework assignment? Anything at all? Any questions that's come up about this? Okay. Okay. So then let's go, and first I want to look at an idea that's going to be it's an idea that helps explain how the scanf function works. So it's a serious folder on scanf example. It's in this folder here. Okay. It's an idea that explains how scanf works, and it's an idea that we're going to be using a lot as we go on. And the ideas were called in, out, and out parameters to functions. Okay, now see this URL? This is a shortcut to the C tutor, which is the C visualizer. If I double click on this, yeah, see, it brings me to a web page with C code. This is a lot like the Java visualizer. It was written by the same people who wrote the Java visualizer. It lets you watch C programs run. Okay. Okay, so we're going to use this to explain. This is a real good way, just like the Java visualizer is great for explaining Java ideas, the C visualizer is really good for explaining C ideas, especially pointers, because it lets you see pointers. It's a lot better than using a debugger in an IDE, because it's even more visual than a debugger would. I mean, debuggers help you see what's going on, but this thing's even better at drawing things. Okay, all right. Now here's an idea. In the C programming language, it's common to have functions where the parameters have three different roles. A parameter can be what we call an in parameter, an in-out parameter, or an out parameter. Okay. Now, what I mean by that is if the parameter is a pointer, so it actually points at a memory location, you can use you can dereference the pointer and put something in the parameter. You can modify the parameter. So an in parameter is a parameter that isn't modified. It just goes into the function and doesn't get changed on the way out. In-out parameters work both ways. So that's y is an in-out parameter. We'll see that it passes information into the function, and then the function uses y to pass information back out of the function. And then z is an out parameter. It's used only to pass information out of the function. It acts as like a kind of a return value. So in a way, the out parameter is a kind of return value, and so is the in-out parameter. The in-out parameter acts as a kind of return value. Okay, now that's the idea we want to get at. Now you can only do this with pointers. You cannot have an in-out parameter or an out parameter that's not a pointer. Okay, so when you see that a parameter to a C function is a pointer, you have to immediately start asking, is that thing going to be used for input, for output, or for both? Okay, now notice that this function has a return value also. So the function has a legitimate return value, and then it has these kind of sneaky return values. And in the C language, these things are used a lot. In-out parameters and out parameters are ubiquitous. And they're one of the things that makes actually programming in C a little bit tricky. So I wrote a little like baby function here that takes three parameters, one in out, and one out. And what the function is going to do is it's going to take the two in parameters, x and y, and it's going to add them, subtract them, and multiply them. Then the sum is going to be outed through the in-out parameter. The difference is going to be outed through the out parameter, and the product is going to be outed by the return value. So this is just to show you that you can do kind of weird things with C functions, okay? Now, what that does is, here's where I call the function. I create a variable A, which holds 5, and I create a variable B, which holds 6. Then I create a variable C that's uninitialized. It doesn't hold anything. It doesn't hold anything right now, okay? Then I'm going to call F. The return value of F will be stored in D. Notice that I'm using the ampersand symbol. That means I'm saying to F, point at that variable here. So the first parameter F points at this guy. So it's the address of this guy. So this guy is a pointer to an int. So in this case, F is going to, we'll see in the picture, X will point back at that variable. Then I pass the parameter, the address of B to the Y pointer. Okay, so Y is something that points at an int, and I'm making it point at B. Okay, and C is being the Z variable is being pointed at the C argument. Okay, now there's nothing in there. And since that's an out parameter, there doesn't need to be anything in there. We'll this function will fill in the C for us. See, that's kind of the interesting thing, is that I don't need to initialize C because it's going to get filled in by calling F with the address of C in that parameter. Okay. Now what happens down here? X points at something. Star X, we call that dereferencing. That says, get me the value in the variable that X points at. Okay, so that's a lot to say. Get the value in the variable that X points at. Okay, that's just that. That's what star X means. Okay, star X means get the value in the variable that X points at. X is a pointer, so X points at something. Star X means get the value in what X points at. Okay, now that's going to get the 5. That'll be put in, well, that'll get the 5. This will get the value stored in the location that Y points at. So Y, now we know that Y points at B, so that'll get the 6. Okay, so that'll add X and Y. Okay, then this will just subtract X and Y. Okay, and this one's funny to read because this one will multiply what's pointed to by X and what's pointed to by Y. And you got to read that real carefully because that's multiplication and that's dereference. If you want to make this even harder to read, do this. Java doesn't care, or C doesn't care if you put spaces between these things. So now you get code that's real unreadable. And you got to be real careful. C can become really unreadable real fast. Okay, that's a perfectly legitimate way to write this. That says dereference X, multiply it with the dereferencing of Y. Okay, now most people will put the star right next to the variable to kind of help read it, and some people will even make it a little bit easier to read this by putting a little bit of an unnecessary bit of grouping there, just to kind of say, I'm dereferencing X. That's not multiplication. Not too many people will group it like that, but sometimes people will to help readability. But almost always people put the star right next to the variable, but you don't have to. You can space it like that. Okay. Right. So this multiplies what X points at with what Y points at. Okay. Now remember, this says dereference. This says give me the address of. This one creates a pointer. This one uses the pointer. Okay. And here, this one declares the pointer. Okay. Now, this star, and this star all have different meanings. They're not the same thing. This one's multiplication. This one is follow the pointer. This one says something is a pointer. This is a declaration. It's not follow, it's telling you what X is. X, a lot of times, now this is a place where a lot of times people do put the space here. A lot of people put the space there. Okay. Okay. And some people write it like this. Because what is X? X is a pointer to int. So there you read it as X is pointer to int. When you do this, it's kind of hard to read this because see, you tend to read this. This is especially beginning C programmers. They misread this. They read this the way they read this, as it's doing something. Okay, it's not up here. This is not doing anything. It's declaring. And what it's declaring is that X is a pointer to int. So you actually have to read this one very weirdly. X is pointer to int. Okay, that's how you read this one. X is pointer to int, which really means that this guy is lumped in with that one. Okay, here, this is doing something. It's saying, get the thing pointed at by X. So get what X points at. Okay, There's a reason why people tend not to write this one and they write this one. And it's one of the confusing aspects of C. Okay, let me go up here and just do something. I'm going to write, okay, int star. Let me write this. What is U? U is a what?
Int pointer.
Int pointer. What's V?
Int pointer.
No,
Just an int.
just an int. This guy is not bound to the int. He's actually in the C language bound to the U. So you read this as U is an int pointer, but V is a skip over the star, V is an int. So that's why people don't do this, because here, this is confusing as all get out, because it looks like you're saying U and V are int pointers, but you're not. You're saying U is an int pointer and V is an int. Okay?
If you put a second star there, would it make V a pointer too?
Yes, that's how you make V a pointer. So the way you would do it, if you want two pointers, you should write it this way. U is an int pointer and V is an int pointer. You have to write it this way. Okay. Similarly, here's another example of something like this. Remember in Java, if you want an array, you do that. But in C, if you want an array, you do this. Because that is A is a array of ints. What's B?
Just an int.
Just an int. What's C?
Int pointer.
Int pointer. Notice how weird this is. This guy is saying that I'm working with ints. This says A is a array of ints. B is an int. C is a pointer to an int. Now, this is, by all accounts, by everybody's agreement, terrible notation. A big, huge mistake. It shouldn't have been designed this way, but it was. Okay. And the reason for design this way has to do a lot with the limitations of compilers back in the 60s and 70s. So we're kind of stuck with this language like this. It makes C hard to read. Okay. You got to be real careful. Now, one rule that a lot of C programmers use is never declare multiple variables on one line, because you can very quickly write real junk that people can't read. So a lot of people would tell you that that should be written as int A array, int B, int star C. You know, keep them on a line each. You know, keep them on a line each. Don't do this kind of thing here. Now, experienced C programmers do, it really varies. Some experienced C programmers say, hey, you should be able to deal with this. And other experienced C programmers say, it's so easy to misread this. And even the experienced C programmers will occasionally misread this, that they'll just say, don't do it. Don't show off. Don't do it. Declare every variable on a line by itself. By declaring every variable on a line by itself, that you can be much, there's a lot less likelihood of getting really mixed up by this kind of stuff. Because this is a real easy mistake. Like, this is too easy to misread.
What if you put a star next to the int? So it's int star star. Would that make B an int pointer?
Say it was a little. Your voice was muffled. Say it again.
If we put a star next, like a second star next to int, so it's int star star. Would that make B a pointer?
Okay. Where? Okay. On line 11.
Yeah,
Put another star where?
right there.
What
Is
does that
V a
make it?
pointer now?
What do you? Okay. What is U?
Wouldn't that make you a pointer to a pointer?
Yes. It makes U a pointer to a pointer. And what does it make V?
An int.
An int. Yes. Got to be real careful with this. Like this is really dumb. Okay. Now I'm really treading on thin ice. What's U?
A pointer to a pointer.
Yeah, U's still a pointer to a pointer. What's V?
Still
int?
an int.
Still an int. Yeah, but I've got code that's going to be, I mean, hopefully my boss will scream at me for writing code like that. I mean, I would hope that hopefully people will not accept you writing things like that, but it's legitimate C. Okay. The proper way to write this would be to do it that way and to preferably put V on its own line like this. Okay. Don't declare multiple variables on one line. The only time it's really okay to declare multiple variables on one line is if you do this, int A, B, C. Okay, that's okay. All right, they're all ints. Okay, there's nothing to be really confused about there. So that's no one's gonna gripe about that. No one's gonna say you shouldn't be doing that. Though some companies do have a hard and fast rule, only one variable declaration per line, only one per line. But this is usually not gonna cause problems. But don't mix up, don't do something like that. Like this. What's W?
Pointer to
pointer-
an int array.
Okay. There's two possibilities. It could be what? It could be a pointer to a
Int array.
array, or it could be a
Array of pointers.
array of pointers. And it turns out it's an array of pointers. You read it from right to left. In fact, as we get along, you'll find out that you read these things in a circular way. You read them in a right, left style that's very confusing. But you read this right first, then left. Okay, you go right, then left. So that's an array of pointers to int. Okay. If you want it to be an array of integer pointers, you have to write it on one line by itself. You have to do int you have to group it. Now it's array of integer pointers. No, that's the same. No, I'm sorry. Pointer to this stuff. See, I want a pointer to an integer array. That was let me see. W is, by definition, W is a pointer to an array. Okay, when we get to arrays, see, to say that something is a pointer to an array is redundant. All arrays are pointers. All array variables are pointers to arrays. So array variables are by definition a pointer. So that is by definition a pointer to an array. We'll talk about that more later on. But so this one is an array of pointers. It's not a pointer to an array because pointer to array is redundant. This is pointer to an array. So we're going to have to spend a little bit of time later on talking really carefully about how arrays work in C, because arrays are very bound up with the idea of a pointer. Like in Java, arrays are reference variables. So it's not too much different than the way Java works. In Java, an array variable always is a reference variable. And that's the same thing in C. Every array variable is a pointer, but it's a pointer in a confusing kind of way. All right. So now I'm going to delete all these because they're not part of the program. Okay. Okay. So again, reading these things is tricky, especially the star. Remember, this star is not this star. This star says, follow that pointer to what it's pointing at. This declares X as an address. X is the address of something. X is a pointer. So the variable X holds an address. Okay. All right. Now, what happens when we run this program? Hey, let's watch it execute. This thing's running slow today. I was playing around with it this morning and it was running really slow. There might be a bunch of people using it. Hopefully it won't. There. Okay. Finally took a while to come wake up. Okay. All right. So it's like, it's like the Java visualizer. That arrow says where we are. So we're at the entry point to main. Notice that the variables have already been declared. In the C language, these variables are actually, well, the way that this visualizer sees it is that when you're at the entry point of a function, the stack has already been allocated. That's just the way they show it. Okay. So at the entry point to a function, they show the stack as holding all the local variables. If this was a Java visualizer, tends to show these variables get allocated as they are declared. So Java would show line 3 creating A, and line 4 creating B, and line 5 creating C. But this one shows you at the entry point, all the variables are already in the stack. The stack is, and that's actually how C language works. The C language allocates the whole stack frame, what's called the whole stack frame, at once. So you're at the beginning line of the main, so you've allocated all the local variables. But see, notice that they're uninitialized. See, they don't have a value yet. Okay, then start stepping through the code. Okay, now A gets its value, B gets its value. Notice it skipped over line 5. Okay, if I go back, notice it skipped over line 5 because line 5 is redundant. The variable's already been declared, but it's not being initialized, so C stays uninitialized. Okay, now I'm about to call F. Okay, notice that I'm at the entry point to F, so all of F's local variables are allocated on the stack. Okay, so now 3 of them are parameters and 3 of them are local variables. Okay, so X, Y, Z are parameters. Notice that they give you a little helpful, it's a pointer. See, the visualizer is kind of clever. They actually point out to you that this thing holds a pointer, and this one holds a pointer, and this one holds a pointer, and this one holds an int, this one holds an int. Notice that what they're showing is that every variable has a type, a name, and eventually a value. Okay, that's an important thing for you to remember. Every variable has a type, a name, and a value. Okay, every variable has a type, a name, and a value. Something you should always be keeping in mind, especially when you do C programming, that every variable has a type, a name, and a value. Actually, it has a fourth thing. It has a location also. So a variable, if this was a real low level debugger, it would show us the address of where X is in memory. Okay, so actually every variable has an address, a name, a type, and a value. Okay, so here's how they show you the pointers in this one. Okay, now F has been allocated, the variables are allocated, but I need to initialize it. Remember, I called F with this guy here. So notice that when I click from line 16 to line 17, it initializes the parameters. See, if I go back, these 3 are parameters. They haven't been initialized yet. They've been allocated, but not initialized. I click next, and they get their initialization. X is the address of A. X points to A. Now, if you were looking at what's in memory, here's what you would see. This variable has actually got 4 things associated to it. It's got a type. It's kind of hard to highlight. It's got a type. It's got a name. It's got a value. It also has an address. Like maybe it's at memory location 1,257,000. That address is what's in this variable here. Here it's shown to you as a arrow pointing from there to there. But if you looked inside the computer's memory, what actually is in this memory location, the value in this memory location is the address of this memory location. Okay, So this memory location has an address, a name, a type, and a value. When you say that X gets the address of A, you're using the fact that the A variable has an address. It has an actual number associated in memory. What is its address in memory? The address of A is what's in X. The visualizer shows you as an arrow, and that's where they get their name, pointers. They point at the memory location. In real memory, there's just a number in here. X holds some number, and that number is the address in memory of the A variable. Okay, same thing with Y and Z. Now, Y points at X and Y point at memory locations that have values. Notice that Z points at a memory location that's still uninitialized. So if Z were to dereference itself, it would just read. Now, here they show as a question mark to point out that it's not been initialized. What's really in there? Does anybody know what's in that question mark?
Is it 0?
It might be. What else might it be?
Null value.
No, actually, 0 and null are the same thing. They're just two names for the same thing. You call it null in some situations, and you say it's 0 in other situations. In Java, it would be 0, but in C and in some C compilers, it is 0. But what else could it be?
Just the memory address?
No. C has an address. So it's a location in your computer's memory. There's something in that location. It can't be empty. See, no memory location can be empty because it's physically a bunch of little bits in memory. They can't be empty. Okay. What could be in there? Anybody have an idea?
It
It's
could
hard,
just
but
it could just have data from a prior program or just any random.
yeah, it's got whatever. It's a physical memory location. What's in it is whatever somebody put in it the last time they used that memory location. From the point of view of this program, it's just garbage or a random. Yeah, somebody wrote it on the chat. It's a random number. What it is it's the last program who happened to be allocated that piece of memory in your computer, whatever they left in it. Okay. So if you don't initialize it, it's just holding what it held a second ago before your program was running. Your program is using memory that was used by some other program, a little while ago, because your computer has a certain amount of memory and this program's running in your memory. And the memory when one program shuts down, another program starts up, the program that starts up uses the memory left over from the program that shut down. Now, some compilers will spend the time to zero out the memory before it gives it to you. So they'll make it so that your program will zero out the memory, but that takes time. So most programmers don't do it. Most compilers don't do it. It's a kind of weird trade-off. It's considered a more secure thing to do, to zero out all the memory that a program is allocated, but it takes time to do that. And so, is the time to do it worth it? And it's going to be more and more common to spend the time doing that. It's going to be more and more common now that the memory your program runs in has been zeroed out by something before it's given back to you, before it's given to you. Up until a few years ago, every time your program was given memory, it was just what was in the memory was whatever was left there by the last program that used the memory. But now operating systems and programming languages are becoming more secure, and they're tending to zero out the memory so that you can't go fishing in memory. There used to be programs that would just allocate memory and see if they can find a password in it, then allocate more memory and see if they can find a password in it, hoping they might stumble on some piece of data that got left in memory by some other program. So, but like this version of C probably is just going to it's an older version of C. It's an older version of GCC. It probably is still going to leave whatever was in that memory location. Okay, so C is uninitialized. What's really, the visualizer reminds you it's uninitialized by drawing a question mark there. your program hasn't put a value in there yet. So it's shown as a question mark, which is kind of clever of the visualizer. Show a question mark for things that aren't initialized. If you ran this in a real debugger, you'd probably see a random number in there, some number that was left there by the previous program. You might see a 0 there because it might be that you're running on a system that does zero out memory before your program sees the memory. Okay, all right. Now we're at line 17, which we're at the first line of this function. The parameters have been initialized. They're pointers, so they're pointing at these variables. Now, X is an input variable, we said. So you read what's in X and you get the 5. You read what's in Y, so you get the 6. And then you add them together and put them in sum. Okay, so sum is 5 plus 6. Okay, and then you read what's in the X and read what's in the 5 and take their subtraction and put that in diff. Then you read what's in X and read what's in Y and take their product and put it in. Okay, now here's where things get a little bit interesting. I'm going to take what's in this variable and put it in what Y points at. So that's saying take this number, take Y, follow Y's arrow to where Y is pointing, and put the right-hand side in what Y points at. Now, notice, see, this Y got something out of Y. This one's putting something into Y because this is on the right-hand side of an equal sign, so it's reading Y. This is on the left-hand side of an equal sign, so it's writing in Y. Okay, so it still means the variable Y points at, but here you're putting something in it. Now that's the out aspect of this variable. Here we used it as its in value. Here we're going to, now watch what happens. See, Y points up here at the B, so we're going to write the sum into B. Okay, so now notice that B is a variable that belongs to main. So main called F, and now main's got its memory changed because F was reaching into main's memory and it's modifying something in main's memory. Okay, and this is the subtle part of it. This variable here got mutated. See, when we called this function, B got changed because B is an in-out parameter. Okay. Then we do the same thing with, well, we don't do the same. Z was only strictly, it's called an out parameter, but we do the same thing. We write one of the numbers into the Z variable. Now Z finally got initialized. The C finally got initialized. Notice that C went from being uninitialized to being C finally got initialized. Okay. Well, why? When I type previous, it's supposed to go back one line, but it went back a whole bunch of lines. So let me see. Next. Okay. I'm at line 22. If I do previous, I should go back to line 21. Oh, that's a bug in their system. It went back to the beginning of the method. Okay. I never saw it do that before. I don't know if it always does that, if there's just like, if there's something funny about this function, but previous means it should go back to the, See how there's two arrows? This is what I'm about to execute. The grayed out arrow is the line I previously executed. So the previous button is supposed to go back from this arrow to that arrow. So previous should go from this arrow to that arrow. See, the red arrow is the line that's about to be executed, and the light green line is the line that just got executed. Previous should take you from this arrow to this arrow. So you should go, so the red arrow should go back to here. But notice that this line's in red though. I don't remember ever seeing that before. And when I click previous, it's going back to that red line there. I wonder if they changed this thing since Customize visualization, new. I wonder if they changed something a little bit. Yeah, okay. I'll have to play around with it. I wonder if they made some little, because I don't remember this, like, see how this line stays red? I don't remember that ever being there. So there's this red line, but then there's this red number. And when I click previous, it's going back to that red number. So maybe there's something that maybe they've changed the way it behaves. Okay, all right. Now, the thing is that C is uninitialized. Z points at C. And when I dereference Z on the left-hand side of an equal sign, I initialize the C. Okay, so C gets its value. And then I return, I'm going to return this variable. This guy here is going to get returned to the return value D. See, D is still uninitialized. So this return value got put in D. Okay, so if I go back, well, see if I go back, it should, see, it went back, when I click back, it went back to this thing here. It's not the back, this one should just go back. Oh, look, there's these little red tick marks here too. Yeah, that's something new. The previous button is probably going back to these red tick marks somehow.
I think when you click a line, it turns it red, because when you clicked line 6, it turned red too.
Oh, you're right. I didn't even notice that. Well, no, okay. I can't click on a line. Well, those are comments. Huh. Oh, I wonder if there's like breakpoint. I wonder if they're supposed to be treating those like breakpoints in a debugger. Oh, and see, now I got those little red tick marks here. Can I turn them off? Yeah. I wonder if that's something like a breakpoint in a debugger. Let me see a previous. Oh, now let's see a previous. Now previous. Oh. Yeah, see, now I'm going forwards and backwards. But if I set a breakpoint, then it goes back to the breakpoint. Oh, kind of clever. That might be real useful. Yeah, that might actually be kind of a useful feature. That's the first time I've seen it. But yeah, so you can, if you set something like a breakpoint, then previous goes back to it. See, I was just clicking on here, not paying attention that I was highlighting these lines. Okay, so if there's nothing highlighted, then it works the way it used to work. Forward, 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 back one step, back one step, back one step, back one step. Notice here that this one came from this one. See, when you called this function, you went from 6 to 16. So previous now goes back to 6, then forward goes to 16. Yeah, so you can go back, back, and forth. Make the call. Okay. So this is if none of these are highlighted red, then it works the way it used to work. It just, next goes to the next line and previous goes backwards. But there's this, it looks like it's a new feature. You can sort of set something like a breakpoint like that. Then previous goes back to that breakpoint. Okay. Okay. Now, okay. Now, I'm here at line 23. That's to them, that's the return statement is not the, it's kind of funny that you would think that the 22 would be the return statement, but the way they kind of do it, they have the visualizer go to line 23, which is the closing brace of the function, and then it returns. Okay, and now D got initialized with the return value of F. And the key idea is that when I call this function, B got changed because it's an in-out variable, and C got changed because it's an out variable. So calling this function returns something to D, but it also returns something to C and it returns something to B. Okay, all right, now we beat that idea to death. Now let's see how it gets used, for example, in C. Okay, so I'm going to close this, and now we're going to look at a scanf. Scanf is famously a function that uses out parameters. Okay. Oh, now let me call up the help page for scanf. Okay. So here's scanf's documentation. Now the scanf documentation is a little bit hard to read. Okay. Oh, in fact, it's impossible to read. See, it just says ... here. Yeah. Okay. Let's go and look at. Unfortunately, scanf is a weird function. I mean, it's not a weird function. It's written in a way that's very common in C, but it's also something that's hard to explain. So you look at the prototype for it, and it doesn't tell you very much. It's an example of where in the C language, usually when you look at the prototype of a function, it tells you everything you need to know about the function. But because of this ... here, the scanf function is actually really obscuring what's going on. So let's go look at the code for a scanf, how it gets used. Okay. Okay. Here I declare 3 variables and they're uninitialized. There's 3 ints. Okay. Then I print a little message to somebody. Okay, please enter 3 integers. Then I call scanf one time with a string that looks a lot like what printf uses. And scanf is like, this is like the mirror of printf. In a printf, this says what to print out. In scanf, this says what to read. This says read an integer. Of course, D would stand for integer, not double, because the people who designed C were nuts. Okay, so of course, %D means int. Yeah, and what is double? Percent what?
F.
F. And I think the F stood for float, but who knows? If D stands for integer, all bets are off what any of these things stand for. So %D means read an integer. Oh, I can't even begin to imagine where they got D for integer. I've never seen any explanation of how they got D for integer. Okay, so this, now in printf, it would mean print an integer. In scanf, it means read an integer. Now, where does it put the integer it reads? Well, what scanf takes are out parameters. So just like our example, I think I shouldn't have closed it. I should, see, these pointers are out parameters. Well, this one was in out and this one was out. So these parameters point at a memory location where this function can deposit a value. That's how scanf works. When you call scanf, you give it the address of a memory location where scanf can deposit a value. So what scanf, the first number scanf reads, gets put into X. Then the second number that scanf reads gets put into Y. And the third number that scanf reads gets put into Z. Okay. Now, in this case, scanf takes 4 parameters: the string, which is called the format string, and 3 out parameters. But that's legitimate too. Now it all of a sudden takes 4. Now that brings up an issue. How many parameters does scanf take? What's the answer? How many parameters does the scanf function accept?
I'm going to say as many as you need.
Yeah, it takes as many as you want. It can take 1,000 parameters. If you have 1,000% Ds there, then it's going to wait for 1,000 parameters here. That's what this ... means over here. ... means as many parameters as are needed by this format string. If this format string calls for 27 inputs, then there need to be 27 parameters over here. If this format string calls for only 1 input, there should be only 1 parameter over here. So the number of parameters over here is supposed to match the number of parameters declared in this format string. So that's why this thing's hard to read, because the ... just means what it really means is an arbitrary number of parameters. So for example, here is legitimate C, but kind of stupid. That's a legitimate call to scanf. What's it do?
It takes 4 integers and puts them in X, Y, Z, and W.
No.
Just the same integer.
No, be careful. Yeah. Now you see, you have to figure out what these things do. What would be, what does this thing say here? Oh, I got an extra percent there. I got it. Okay. What does the format string say?
It's only reading 1 integer.
Yes. Okay. So that 1 integer gets matched with this parameter. What about these parameters?
There's no
Nothing
integer
happens.
to read.
Pardon me?
Nothing happens.
Do they just get ignored?
They're ignored. Yeah. It's legit. You're not going to get a compiler error. You're not going to get a warning saying you only asked for one input, but you gave me 4 parameters. Yeah, you only asked for one read value, but you gave me 4 parameters. So the compiler is not going to warn you. It's just, it'll just ignore these. Now, what's a more insidious problem is this.
It'll wait for more parameters that never come.
I'm not sure. I think what happens is the program probably crashes. That the compiler, we'll try it in a minute. The compiler will probably not realize there's any problem here. The program will be told to read in 3 ints. It'll read the first int and put it in that parameter. And probably what's going to happen is that it'll read the second int and put it in a garbage place, and read the third int and put it in a garbage place, and probably crash our program. C is notoriously weird. It'll do bizarre things. Okay, this is probably this is probably not going to work, but you won't get any kind of error messages. Okay, now let's go ahead and try. Let's go put it back the way it was to begin with. Okay, this is the way it was. Let's run it for a little bit. Let's try it out. Okay, now to run this, I need to compile it. Okay, now on my computer, I've got this. I've done what I've told you to do at home. I've got my CS302 folder down here. What I'm going to do is I'm going to make a whoops. In this folder where my code is, I'm just going to make a shortcut to this compiler, so I can just close that. Okay, so this is the way I like to do it. Now I can just drag and drop that program into that shortcut. That shortcut points at the editor, which is with the compiler. Okay, now I can just say compile. Okay, now I'm going to run this program at the command line, because these programs are really pretty much command line programs. So I'm going to open command prompt here. Remember, I gave you a shortcut. I gave you a link to where you could put this command line here on your computer if you want to. It's really useful. This open command window here is really great to have. So I think I would recommend that you put it on your computer. It's really nice to be able to just say open command window here. Okay. All right. So I've got this program compiled, and now I want to run it. Okay. You know what that delay was? Do you see how long it took that program to start up? Did you see the little pop-up window? The virus scanner the virus scanner stepped in and probably examined this program in memory to make sure it wasn't a virus. Okay, so when I ran this program for the first time, the virus scanner kind of stepped in and said, we got to make sure this is legitimate. Okay, now here's my integers, 1, 2, 3. Oops. Okay, their sum is 6. Okay. Okay, now let's play around. Okay, now that was real straightforward. Okay, I declared 3 variables and I read in 3 things. Okay. Oh, and let me run this again. Notice that here's one integer, here's another integer, here's another integer. Okay, notice I don't have to put them on the same line. Here's one integer, here's a second and a third one. Notice it doesn't really care how I put them. Okay. Okay. Yeah, it kind of waits until there's 3 integers. Yeah, it doesn't matter how many times I hit enter. It doesn't matter if I put the numbers all on one line or not. It's scanf is doing what? Scanf is waiting for 1, 2, 3 integers. First one goes into X, second one goes into Y, third one goes into Z. Okay. And it doesn't, so I didn't need to initialize X, Y, and Z because they're going to get initialized by scanf. Okay. Now let's play around. Let's do the one where Okay, ask for 3, but only give 1 out variable. Okay, so, oh, I got 2 editors open. That's confusing. I shouldn't have my code open in 2 editors. Notice that this editor is smart. It knows that I changed the code in the other editor, and it asked me to reload the code. Very good. The good editors will do this. Good editors pay attention to whether you've got your file open in some other editor. Okay, so I say, yes, reload the file. Okay, so there I've got only 1 out parameter, but I'm asking scanf to scan 3 numbers. Okay, so recompile. Okay. Oh, no, the compiler did figure this one out. I'm sorry, the compiler did. No, actually, well, the compiler figured it out, but what?
Prevented you, it's marking it as an actual error instead of just like a warning.
No, it's marking
Oh,
it
no,
as
it is a
what?
warning. My bad.
Yeah, no, now notice that, see, I'm going to delete, close this window. Okay, there, no, I deleted the exe file. Tools, GCC. It compiled. I got a helpful warning, but it's a legitimate C program. So let's see what it happens when I run it. Now, the compiler is smart enough to warn you that this is not very good idea, but it doesn't stop you from doing it. It just issues a warning. One of the features of the C language is you can tell the compiler, make warnings into errors. And that's actually a pretty common way people write their C programs. They make it so that warnings are actually errors, so your program won't compile when you have warnings. Your goal in C should always be to have warning-free compiles, because warnings can be real errors in C. So this is a warning that really is an error. Now let's see what happens when I run it. Okay. The virus scanner needs to recheck it. Blah, blah, blah. Boy, that's annoying. There, fine. Okay, this virus scanner said you're legitimate. Okay. 1, 2, 3. Where's my output?
It didn't give it. It just crashed and said you figured it out.
Yes, it crashed. The program crashed. The program did something really weird. What it did is it read in these integers, and who knows where it put them. It actually put them someplace. I don't know where it put them. Scanf did something. You told it to read 3 integers. You only gave it 1 out parameter. It went ahead and read the other 2 integers. It put them somewhere, and wherever it put them, it overwrote something important, and it's crashed the program. And notice that there's no error messages, no warnings. It just blew up. Okay, run it again. Okay. See, right? This is C is a fun language to work in. Okay, that's a facetious argument. C is a mess. Okay, but all our operating systems are written in C. All our operating systems are as buggy as can be, and all our operating systems are hacked endlessly by hackers because it's hard to write really good code in C. It's so easy to screw up in C. It is really easy to screw up in C. And that's one reason why our operating systems aren't as secure as they ought to be, because it's so easy to do weird things in C. Programs, compilers give you warnings, but say, well, I'm only warning you, but I'm saying you really shouldn't do this, but I'm going to go ahead and let you do it. Then your program does something bizarre and crashes, but you get no error messages. Yeah. Okay. And that's the problem with C. Okay. If I do, here I've asked for 3 ints and I give it room for 2 ints. It's probably still not going to work. Yeah, it still crashed. Okay, it still crashed. Yeah, I gave it room for 2 of the prompts. I prompted it for 3 and I gave it 2. Okay, now what happens if what if I prompt it for 1 but give it 2 parameters or even 3 parameters? Okay. Compile it. Now, notice I still got a warning. And it's correct. I'm asking for one parameter, but I'm giving it 3 out parameters. Okay. What's going to happen here is it's going to read, it'll probably read one integer, put it in X. It won't do anything with the Y and Z. Since I didn't initialize the Y and Z, when I add them together, I'm going to get a garbage number. So that's what I think is going to happen. It won't crash. It'll read one number. Actually, it will read only one number. As soon as it's read one number, it'll return with that number in X. Y and Z will be left uninitialized. Then when I add them up over here, I'll just get a garbage number. So let's try it. Okay, 1, 2, 3. See, their sum is blah, blah, blah. Okay, so what happened was the X and Y are just holding garbage numbers. Okay, now I can, now here, if I initialize that and initialize that, now run it again. Boy, it's annoying to have that virus scanner pop up like that. Okay, there's the first parameter. Okay, now the sum is 5 because this time I initialized the Y and the Z so that at least this didn't do anything. I mean, when there wasn't anything written into Y and Z here, I already had legitimate values in there. Okay, right. So I can, so you know, people tell you should always initialize your variables, but a lot of times when people are using scanf, a lot of times they don't initialize the parameters to scanf. Like since scanf is using out parameters, a lot of people do not bother to initialize the variables for scanf. Even if you initialize them, it doesn't really help you much. No matter what I put in Y and Z, that doesn't help me figure out that I got a bug in this program. The real problem here is that, notice that I've got a bug in my program. I'm asking for one parameter, but I'm giving 3 parameters here. The compiler warns me, but it doesn't stop me from doing it. Okay, all right. Now, what about the return value of scanf? Notice that scanf actually does have a return value. Remember in our example, our function here had an in parameter, an in out parameter, an out parameter, and a, well, and this is an in parameter, this is an in out parameter, this is an out parameter. Oh, how do you know that this is a, notice that they're all pointer to int. How do you know that this one is an in and this one's an in out?
Because X doesn't have anything written to it. Y is.
So how did you, so what's the answer? How do you know that this one is in and this one's in out?
You read the method.
You read the method, right? You don't know until you read the method. Now, or you could read what?
Your comment.
Right. You could read the documentation. That's where comments become really important. Comments are important. I tell you here that X is an in, Y is an in out, and Z is an out parameter. And good C documentation will document that. It'll tell you which parameters are in, which parameters are out, and which parameters are in out. Because they could just look like, you know, they all look the same here. And then here is the real return value. See, there's the real return value, but this is an out parameter and this is an out parameter. So there's 3 outs, out from Y, out through Z, and out through here. The documentation is supposed to tell you that. Now you can always read the code. You know, you can find out by reading the code, you can find out by reading the documentation, but what you can't tell is the declaration. Unfortunately, the C language, the declaration does not tell you if that's an in parameter, an out parameter, or an in out parameter, because it's all written the same way. Okay. Now the scanf function really has, now scanf has these out parameters, but then it has a real return value. Okay. Now what is the point of the return value? Okay, now watch this. I'm going to go ahead and put 4 parameters in there. Okay. Compile it. Now I'm going to do something interesting. I'm going to run the program. Blah, blah, blah. Wait for this guy to say it's okay. Okay, I'm going to enter 1 parameter, a 2nd parameter. Now I'm going to tell the C language there's no more parameters. I'm going to send it the end of data signal, which in Windows is Control Z. On Linux, it's Control D. Okay, hit enter. All right. Now, see this thing, RV equals 2? RV, I use that as a variable meaning return value. We asked Scanf to read 4 numbers, but it hit end of file after just 2 of the numbers. So this return value is how many things it actually read before it hit end of file. See, it hit 2 return values. Now that meant the X and the Y got filled in, but that meant the Z and the W are still not filled in. That's why I got a garbage number here. Because when I went and added, well, in this case, I added the Z. I forgot to add the W. But when I added the Z was still holding a garbage value. So here's adding the W. Okay. So X got filled in, Y got filled in, but then the Control Z said end of data. So Scanf stopped reading and it said, I read 2 things. So this is how Scanf lets you know when it reached end of file. End of file is that it read fewer things than you asked it to. Okay, this is real important. In Scanf, end of file is when it tells you I read fewer things than you asked me to. Okay, watch here. Let's do it twice. Okay. Oh, so yeah, let's do the whole thing twice. Okay. Okay, now if I run this, okay, and it wants 4 numbers now. 1, 2, 3, 4. Now it has 4 more numbers. 1, 2, 3, 4. Okay. Now let me run it again. 1, 2, 3, 4. Now I'm going to type Control Z. There's no more data. Okay. And this time I got a return value of -1. It's kind of weird. Instead of returning 0, now what happened was the second time through, it didn't read any of these numbers. Okay. And it returned, I thought it was going to return 0 because it didn't read any numbers, but it returned -1. Okay. You have to read the, yeah, I thought it was going to return 0 because I hit Control Z after the 4th number. So the second time around, there was nothing to read. So I thought it was good. Now let's run it again with 1, 2, 3, 4. Now give it 1 number. This is the second time around. Now Control Z. See, now it said I read 1 number. See, notice how it said it read the -1 was another way of saying end of file. It's kind of, the scanf function's a mess. See, when it read 0 numbers, it returned -1. But when it read 1 number, it returned 1. So when it returns when it reads no numbers, you'd expect it to return 0, but instead it returns -1, which is another way of saying end of file. Okay. Now notice that if the number it returns is less than the number you asked for, that's end of file. If the number it returns is smaller than the number of things you asked for, the only way that can happen is it ran out of data. So it gave you an end of file. That's how you detect end of file. That this number here is less than what you know this thing is asking for. Okay? Or -1. Okay. But -1 is flaky because -1 only means that it didn't read anything. Okay. And that's not the same thing as hitting end of file, because see, you can hit end of file in the middle of yeah, I can request 4 numbers, but I can hit end of file after 2 of them. Okay. So that's different than reading no numbers. That's reading fewer than what you asked for. End of file is when you get fewer numbers than what you asked for. Okay. Now, so notice there's a whole lot of stuff going on here with scanf. The real outputs are these out parameters. This output is kind of a message, just just a little piece of information saying this is how many of these things I was able to read. You use this thing to detect when you've got to the end of your data, when this number is not the same as what you knew. You have to know how many things you're asking for here. Okay, you have to know that you're asking for 4 things. So if this is less than 4, you got end of file. Like over here, if I ask for 3 things here, so if I ask for 4 things here, and I ask for 3 things here, here end of file is when RV is less than 4. Here end of file is when RV is less than 3. Notice that can be really confusing. Here in this scanf, if I get anything less than 4, it means I hit end of file. In this scanf, if I hit anything less than 3, I have end of file. Now, if I get a -1, that always means end of file. That means scanf wasn't able to read anything. But if I ask for 3 things and it reads 1 thing, that's because I hit end of file. No more data. It makes programming with scanf a little bit tricky. Okay. But in general, what you do is you think that end of file for scanf means that you asked for so many things and you got back fewer of them. Now, some people simplify this by never asking for more than 1 thing at a time. Okay. Sometimes, a lot of times, the way you use scanf is this way. You ask for 1 thing and 1 thing only at a time. Okay. Okay. Then you either get back 1 or -1. 1 means you got your number. -1 means there wasn't anything there. Okay, so some people simplify scanf by only scanning for 1 number at a time. But in a lot of but that's just to keep things simple. A lot of C programs don't work that way. They use scanf the way it was meant to be used. They'll scan a bunch of things at once, and then they have a bunch of out parameters, and then they just have to keep track of how many things they were requesting and how many things they got back. So to keep things simple, you can always just request for 1 number at a time. But a lot of people don't keep it simple. A lot of people use scanf to its full, you use all the features of scanf. They do things like this. Okay, but notice how you work. You have to create the location to hold the return values. Okay, you have to create the location that's going to hold the return values from scanf. They have to be declared before you call scanf. Okay, so scanf's kind of weird to use. Okay, and it's a good example of a C function that's using this idea of in-out parameters. Where is it? Oh, I'm up here. It's a good example of a real C function using in-out parameters. Well, in Scanf, their case, they're out parameters. And as we go through this course, we'll see more and more examples of real C functions that make use of in-out parameters and out parameters. It's weird that sometimes people do this. They use a parameter both for input and output. Usually people either have in parameters or out parameters. The in-out parameters are a little bit more unusual. They're not that common, but there are occasions where you'll see real C functions where a parameter is used both to read input into the function and to get output from the function. In the case of scanf, the scanf is only using out parameters. Scanf uses out parameters. It uses 1 in parameter, that's the string. The string in scanf is an in parameter, and then the other parameters are out parameters. Okay, all right, so that's a little bit of playing around with pointers and a good example of where pointers get used. And then on let's see, today's Wednesday, so we meet again on Monday. On Monday, we'll do a few more examples using pointers. Okay, we'll look at a little bit more example of Scanf, and we'll look at some more examples of some code that uses pointers. Okay, and we've run out of time. So, okay, so if you have questions about the homework assignment, please send me emails. So, if you have any kind of questions at all, send emails. Read chapter 6. Even if you feel pretty comfortable with pointers, I think chapter 6 is pretty good. We're going to use pointers more than you probably have used them before. We're probably going to be making more use of pointers than you have in like certainly in 160, in 124, and maybe more than you've used them in some other classes, unless you've done a lot of C programming. Okay, so if you do a lot of C programming, you do a lot of pointers. So we're going to use a lot of pointers. Okay. Anybody got any last second question? Any question
On
at
the
all?
homework,
Pardon me?
on the homework, are we supposed to use a while loop to continuously get input from scanf, or?
Well, yeah, but you have to check for the end of file. Your while loop has to stop when there's no more data. So that's why that's where this trick here, you have to do something where you have to figure out, did I get to the end of the data? Because RV was either -1 or less than what you asked for. So you need a while loop, but your while loop has to be looking for end of file. So essentially it's while not end of file, read another number. So your for loop roughly should be while not end of file, read another number. But you have to find the end of file. You have to know when to stop reading numbers. And in the homework assignment folder, look at this folder here, Scanf and end of file. Read these. Scanf is tricky when it comes to end of file, but I put a bunch of links to these are little a bunch of different explanations of Scanf and end of file. So look at those. These are links to just web pages. Oh, that one's okay. That's the C. I forgot that book has disappeared from the internet. That's the book we're using as a textbook. So that's actually the section chapter 3 from the book we're using, Programming in C. So that book recently disappeared from the internet. I don't know what happened to the people, what they did. Maybe the guy who wrote it retired and his website got deleted by his university. It was at University of Hawaii, and it recently disappeared. Okay, that's kind of bad. Oh, the reason you can read it is I put a copy of it on my website. I took his book and put it up on my website, which is illegal, but until they stop us, I'll keep it up on my website because it's a really nice book. Okay, but these are links to explanation of end of file. Okay, so you write a while loop, while not end of file, read another number, and this should help you figure out how to do that. Okay, other questions about homework or anything? Okay, so I'm going to go ahead and stop the sharing, and we'll meet again on Monday. We'll meet again on Monday. Have a nice weekend. Bye.